Hello everyone. Loads of people here again. Mm. Right. First things first, sorry we're slightly late. If anybody has any questions specifically from the homework, then feel free to send them to me. I will just be starting in just a minute or so, if you just bear with me for a moment. Right, no specific questions so far. So what I'll do is I will do a little recap of some of the important parts of some of the physics topics that we have been doing in the last week or so, mainly focusing on forces, which everybody in year 9 and year 10 did, but year 11 didn't. But that is the main thing that I will focus on. If you do have any specific questions with regards to the homework, I do have it open here, so feel free to ask as we go. Um, yeah, and let me know if any issues. Oh, we've got some questions. Um, Question one. Yeah, nine. All right, let's do that. And then we'll work backwards from some questions. Um, okay, what's this? The anonymous attendee question. If you could come back with the name, then I will answer that question, if that's all right. Um, about the 5D question. Right, so question one on this homework. Okay, let's talk about this then. A normal contact force. Right, I will answer all of these questions. Don't you worry. So I'm also not in any rush today, so we can drag this out if necessary. Part of a bus route. So this is a distance time graph. It's kind of question. Okay. There are a few things about distance time graphs that you need to be familiar with. For example, what do each of these different sections actually tell you about what is going on in terms of the movement of this, whatever it is? It's a bus. So I'll tell you the first things before we move on to the actual question. Going from A to B is a constant speed. So when you have a straight line that's diagonal, it means a constant speed on a distance time graph. Now, the steeper that line is, the faster you are going. So when I say constant, again, just to be clarified in case anybody has any misconceptions about this stuff, um, the a constant speed means your speed just stays the same and never changes. Okay. So on this journey, on this part of the journey, the speed stays the same and never changes. We can actually work out what the speed is by doing distance divided by time, should we need to. But as I say, the steeper this is, the faster you're going, which means that D to E is also a constant speed, but because this is not as steep as A to B, it means you're not going as quickly. B to C, that bit there, when you have a straight horizontal line on a distance time graph, it means you've stopped. With that information, we should be able to answer these questions. The bus travels slowest between D and E. How can you tell from the graph? Well, it goes slowest at the point where the line is the least steep. Okay, so it's slowest between D and E. How can you tell from the graph? Because D to E has a, it's less steep would be enough for the mark, but also the proper correct answer is that it has a smaller gradient. So that would be so that would be the answer to that question. Okay, so between which 2 points was the bus traveling the fastest? So again, as I say, the fastest part is the bit where the line is the steepest. That looks to me like A to B. A to B is the steepest part of this graph. So between A and B, you're going fastest. So that should be A to B there. There is a bus stop on the high street marked as point B on the graph. What is the distance between A and the bus stop? So that's where the bus stop is, where the B is. The distance is 200 meters, isn't it? Because it's just in line with 200. And that is your answer to that question. And how long did the bus stay at the bus stop? Well, it's however long the line was flat for. So what you have to do is just be a little bit careful with your lines here. That started at 40 seconds and then it finishes at 60 seconds, which to me suggests that the time is 20 seconds. It's between 40 and 60. So yeah, if you want to show clearly how you work out your answer, you probably need to say 60 take away 40, or whatever those two numbers were to get us to 20. And then a cyclist made the same journey along the high street. The cyclist started at the same time as the bus and completed the journey in 200 seconds. He traveled the whole distance at a constant speed. Okay, so if you're going at a constant speed, your graph looks basically a straight line that looks like that. So completed the whole journey in 200 seconds. The journey was finished here, right? It was 500 meters. Now, if it's traveled at a constant speed the whole way, then use a ruler. I don't have a ruler right now, but actually I do. Um, yeah, okay. Then all you need to do is draw a straight line that goes from there to there in order to answer that question. And that is all of question one. I'll just see if there's anything else on this booklet that doesn't seem to be. So I'll go on to whatever the other one has been asked. The first question. Um, What is a normal contact force? It's on question 3B. Let's just have a look at it first, and then I will explain. A normal contact force is usually, at least while I get to the question, is usually the force that you, for example, if you sit on a chair, then there is a normal contact force upwards from the chair upwards to keep you there. Okay, so that's what a normal contact force is. If you push against a wall, there is a normal contact force which goes back the other way. That's usually what it means, but I'll have a look at the question. So question 3B. Which arrow represents the normal contact force? So yes, in this case, the normal contact force has to be C because this skier, as it were, is pushing down and the surface is effectively reacting back upwards. That's why it's called a reaction force. It's reacting back upwards to keep that person where they are. So that's what the normal contact force is. It should be C. Um, does it always go upwards? Well, no, it does in this case because the contact is between this skier and the surface, and so the surface reacts upwards because the skier is pushing down. It is essentially in the opposite direction to the existing force. So if you were, I don't know, if there was a wall and somebody was pushing against the wall in that direction, there'll be a normal contact force the other way. So no, it's not always upwards, but it just depends on the situation that you're describing. Um, so hopefully that answers that question. Question 7C and 7D in the year 10 one. Again, there's somebody asked me about question 5D on the year 10 homework, but I'm not going to answer it until I know who it is. 7C1, 7C1. Okay. Okay, so question seven, C1. Okay, slightly more complicated question, this one. But I might just do all of question seven so that we have got it. I'll just get the answers ready. Yeah, no, in question two. Yeah, I'll get back to that, I'm sure. Okay, so question seven. Let's just go through this from the beginning. The diagram shows how the thinking distance and braking distance of a car add together to give the stopping distance. If I just do a little recap of the stuff that you should have covered in the lesson, this whole stopping distance begins when the driver sees the hazard. So if there's someone that's run out in front of the road, for example, that would be a hazard. So it begins at that point when you see it. Once you've seen it, the next thing that you need to do is get to the brakes. Now, your car will be moving while you process that information. So, because we all have a reaction time. And in that time, you will travel a certain distance. That distance is called the thinking distance. And then when you press the brakes, again, when you press the brakes, you don't just stop instantly. You keep moving because you're slowing down. And then that distance that you cover while you're slowing down is essentially your braking distance. And those two distances add up to give the stopping distance. The stopping distance is found by adding the distance the car travels during the driver's reaction time and the distance the car travels under the braking force that should be, because that's what the braking force is. What's happening is when you press the brakes, there is a force essentially the other way, and that during that time, your car is still moving. So that's A at least. Which of the following would not increase the thinking distance? The driver being tired would increase the thinking distance because it means that you'll have a longer reaction time. The car being driven faster would also increase the thinking distance because the thinking distance is affected by your speed and your reaction time because distance is speed times time. Let's not forget. So if you are traveling faster, even if you've got amazing reactions, you will go further. Um, the car tires being badly worn affect your braking distance because they will increase, they'll have less friction perhaps, and therefore you will go further before you stop. So they affect the um, braking distance rather than the thinking distance. And then the question you actually asked is part C. The graph shows how the braking distance of a car changes with the speed of a car. The force applied to the car brakes does not change. What conclusion about braking distance can be made from the graph? Well, the first most obvious mark to say is that clearly the graph shows that as you get faster, your braking distance increases. So I would definitely say that first, that braking distance increases with speed for a start. Okay. Um, that would be the most obvious thing. You can mention the words positive correlation if you wanted to do that. But then what you need to say for how many marks is this? Two. For another mark, with any graph that isn't a perfect straight line, you need to sort of understand why it's not a straight line. So, for example, you want to explain the reason this is not a straight line is essentially because at lower speeds, your braking distance increases more slowly. It doesn't increase as much. Whereas at higher speeds, you can see the line gets steeper. So it's sort of, if we broke it into two pieces, it would be like that one line and then that another line. So it's steeper further on, as it were, which tells you that your braking distance increases more at higher speeds. So you could say something like that it increases more quickly after, let's say, 15 seconds or something like that. So at 15 seconds, it seems to start getting steeper. What else could you say? You could also have said, um, I mean, technically, you can also say that when you double your speed, your braking distance actually gets four times bigger, as this graph sort of shows you. So at 10, your braking distance is 10, but at 20, your braking distance is four times bigger. That's actually true. That is what actually happens. We'll check if I'm missing any questions. How can the car being driven faster affect your reaction time? Okay, good question. The answer is the car being driven faster does not affect your reaction time. But what it does affect is your thinking distance. This is a common confusion, this is that your thinking distance is not the same as your reaction time. They are two different things. Okay. The thinking distance is how far your car travels during your reaction time. So if your reaction time is, let's say, 2 seconds, then your car will travel a certain distance, right? If your reactions are slower due to alcohol or any other factor, then your reaction time might be longer, which means your car will go further during those same 3 seconds. But let's pretend there are two drivers, okay? Both of who are driving along and suddenly, I don't know, a child runs out in front of the road. Let's say they both have exactly the same reaction time. So let's say both their reaction is 1 second. Let's say 1 second, 1 second. Now, if driver A is driving at 100 miles an hour, now during that 1 second, they're going to go much further than if driver B was traveling more slowly, and that means he would get to the brakes sooner. So you'd have a smaller thinking distance. Nothing to do with those things that affect your reaction time, but just by going slower, it means you will cover less distance in the same time. And that's a common confusion, which is your thinking distance is not the same as your reaction time. It's affected by your reaction time, but it's affected by speed as well. Because from the physics equation, distance is speed times time. Hopefully that clarifies. Um, so the remainder of question 7 over here. There's no need to ask me the question 3 times, if that's all right. What conclusion about braking is going to be made? We've done that, right? Done that effectively. The graph is for a car driven on a dry road. Draw a line about what is likely to happen to the braking distance at different speeds if it was driven on an icy road. Well, look, the best way to do this is to go, if I was traveling at 10 meters per second in dry conditions, then my braking distance is 10 meters. What would you expect to happen to the braking distance if you were driving in icy conditions? Surely you expect it to be higher, right? So I would say that for my new line, the braking distance is going to be bigger at the same speed, and it's going to be bigger at every speed. So essentially, your new line just needs to be above the previous line. That's all it needs to be, just above it. Okay. Right. I'm just going to do something. Just give me 1 second. I'll be right back. Right. Just to clarify to the person that asked a question 4 times, if that kind of thing happens again, I will immediately remove you from the call, if that's okay, without further thought. Can we do a question about on calculating acceleration from a velocity time graph, please? Yes, I'll do that. What else do we need to do? The graph is, we've done that, right? Done that. A local council has reduced the speed limit from 30 to 20 on a few roads. The reason for reducing the speed limit was to reduce the number of accidents. A local newspaper reported the following. It will be much safer because drivers can react much faster when driving at 20 miles per hour than when driving at the statement is wrong. Okay, because your reaction time is not affected by how fast you are going, is it? The reaction time doesn't depend on the speed. Your reaction time is what it is. It's got nothing to do with how fast you're going. Again, this goes back to that previous confusion, which is that sometimes people link thinking distance and reaction time like they're the same thing. They're not, they're just related, I suppose. So in this case, your reaction time has got nothing to do with how fast you're going. Your thinking distance is affected by your reaction time and how fast you're going, but they aren't affected by each other. So what I would say here is that your reaction time does not depend on the speed of the car. Okay. Then, last bit of this, the local council must decide whether to introduce the lower speed limit on a lot more roads. What evidence should the local council collect to help them make this decision? Um, Whether to introduce the lower speed on a lot more roads. So what have they done so far? They have done it on a few roads so far. They're trying to figure out whether they should do this on more roads. Well, what they need to do, because what was their aim? The reason for reducing the speed limit was to reduce the number of accidents. So surely what they need to do is on that road that we have just reduced the speed limit on, we want to monitor if the number of accidents has changed before the increase or the decrease and after it, right? So what we want to say here is something like that for let's name a time period, let's say, so for 1 year, let's say, or for 1 month, compare the accidents before and after the lower speed limit was introduced. Because surely what you want to do is figure out whether this has actually made a difference. Has it worked? This decrease in speed limit, has it resulted in more accidents? Because only then will you decide whether to introduce it to more roads. So you need to know, how many accidents were there in the month before we did the change and how many accidents were in the month after. You need to mention the time period specifically. There was one more question on the year 9 one, which I will just check on. No, I'm just going to go back to which was number 2. I mean, it's quite easy, this, but the first question is, what is the total force on the trolley due to the adult and the child? Well, the child is 10, the adult is 40, I presume, it's that way around, which is 50. That's it. Which one of the terms means the same as total force? Basic resultant force is what we generally call the total force acting on an object. And then there is a formula for this, which I appreciate. If you don't have it, then it makes it a little bit harder. But work done is force times distance. So if you want to calculate work done, you use the force, which we know is 50 from the question, times the distance, which you know is 80, and then you multiply those, and you should get the answer. You should put, even though I don't think you need to, joules, because that is the unit for work done. It is the same as energy transferred. Oh, that's it. Sorry. That was the next question. And then most of the work done to push the trolley is transformed into, I think it should be heat. I'm not going to check that, but it usually is. Right. Is there anything else? Question 5D. Um, Question 5D. Oof. That is a complicated question. But I'll tell you, because you may not have done this one, but this is a moment question. It shouldn't have really appeared in this one. But moment is force times distance. There is a formula that you'll get given. And the distance D marked on. I think we use that formula. I'll just get this ready. So the problem is, it's hard to do this question without a previous one, but there is a moment given to you in that question, which I appreciate. If you haven't done this, this will be almost impossible to do. But the moment from the question is 13,800. The force from the question is 11,500 because it tells you in the diagram. And so to calculate the distance, you do this divided by this, right? So that would be, it's just about taking the numbers out of the question and dealing with it in that way. Can you please do these topics? Energy, electricity, particle model, matter, atomic structure, AQA. The answer is no, we're not going to do all of those topics. In answer to any other questions, I mean, I can recap some of them, but I'm not. We are literally doing. Is moment the same as momentum? No, it's not. Sadly, momentum is a different formula. Moment is a different thing. You may not have done much of this yet, so don't worry. It's just that They are different things. So momentum has its own formula. It is mass times velocity, which is what momentum is. A moment, I've not written this very well, but a moment is has its own formula, which is force times distance, as we just did. But it's the moment is the best way to think of moment is think of a screwdriver. What does a screwdriver do? It basically helps provide the turning force, right, to open things or close things. So that's what a moment is. It is a turning force. It's to get something to rotate, essentially. Um, and it's a different topic. I mean, it's still within forces, but it is a different topic. And as I say, we over here do um, different topics. We do forces again, so we cover some of the later topics later. But if you do need anything else, then let us know. Um, okay, and then that was that. And then I mean, nine work. What unit would we use for distance? Distance should always be in meters. In any physics question, it should always be in meters. Um, and then somebody asked me about question 6 on here. Um, so which of these blocks has the smallest weight? That should be C, shouldn't it? Just because it's the lowest, the highest up, as it were. Um, and then we have a life buoy next to a swimming pool. It has a mass of that. Da, da, da. This should again be easy. All you do is take the mass of 2.5 times it by gravitational field strength, and you should get the weight. That should all be straightforward. When thrown into the water, the life buoy floats. The two forces are the weight of the life buoy downwards and up thrust upwards. How big is the up of the life buoy compared to the weight of the life buoy? Look, right. So in any situation, if something is not moving in a particular direction, then the forces on it must be equal. They must be. So what I'm saying is, if I don't know, if there was a box and somebody was pulling that way and pulling that way, and the box wasn't moving, doesn't it mean that they must be equal? It's a bit like a tug of war situation, right? If it's not moving, then the forces should be the same both ways. Similarly, if something is floating on water, like these things, let's say, then if it's not moving up or down, right? If it's just kind of staying bobbing where it is, then whatever the downward force is must equal whatever the upward force is. Because if this was bigger than the upward force, surely this would sink, right? So this is the crucial thing. The crucial thing in forces generally is that if something is not moving or moving at a constant speed, in other words, it's not getting faster or slower, it's just staying as it is, then the forces on it must be equal. So when this question says that it floats, right? How big is the up thrust compared to the weight? So in other words, how big is the upward force compared with the downward force? They must be the same if it's not sinking or flying, I suppose, right? It's got to be the same. This is a formula which is resultant force equals mass times acceleration, which you will get given, so I can tell you that. And then this question, again, if you use that formula, resultant force is mass times acceleration, should be relatively straightforward. The resultant force is 4, the mass is 2.5, and therefore the acceleration you find with a bit of maths by dividing over. Um, isn't the upthrust greater because when you push it down, it will go straight back up? Well, no, because that's a slightly different. You're asking a different question. You're saying when you push it down, will the upthrust be greater? That's it's that you've changed the situation. The situation right now is that this thing is floating, so it is not moving up or down, which means the forces at that point are equal. When you push it down, then at that point then let it go. So let's say when you push it down and then let it go, at that point the upthrust is bigger than the weight. That's what causes it to go back up. So you've asked a question, but you've changed the situation. You see what I mean? Um, okay, was there any other questions that I can see immediately on here? Done that, done that. Okay, let me. I don't think there's any other questions, I think, on the. So did did normal contact force. Seven, did all of seven, didn't we, on that one? Yeah, I appreciate some questions were in both. So hopefully we've covered some anyway. Um, okay, right. In that case, make sure that nobody else has added anything. Um, Year nine booklet number 5B. I think I've done 5B. Oh, I thought I did. Um, okay, I mean, I'll just tell you the answer. It is the same answer as that one. The idea of this is that it's basically the same as any force question. It's like if you want something not to move, in this case, not to topple over, the forces have to be the same. So it is actually just the same answer to that question. And then the only other question, last one I'll do from this one, number 16. Is there a 16? Where's 16 come from? There isn't a 16. So no, be the answer to that question. Um, I'm not doing any more from this one. I think that's enough assistance for you. Um, Six. I think I've done six from this one. Yeah, I've done number six. I've just literally just did number six. If you have just joined, then you've missed it. Sorry to say. There will be a recording. You can watch it later if you want, but I've just done question six on that one, so no. Um, is there anything else from this that stands out to me that I should talk about? Yeah, so somebody did ask me about acceleration from a velocity time graph. That was the specific question somewhere. Question on. I can't do a question on it. I want to make this up myself. But right, a velocity time graph. I mean, it is surprisingly it's not that difficult. But let's pretend this is a velocity time graph, and I'll make up some numbers in relation to it. Um, let's pretend that's 10 seconds, and that's 20 seconds, and that's 30 seconds there. And let's pretend that this speed obviously is zero, and that's 30, and that's 70, just for the sake of making up some numbers. Um, right. If I said that this was A and this was B, C, and D, let's just say those. Now, let's pretend the question says to work out the acceleration during the first 10 seconds, or alternative, the acceleration between points A and B, which is the first 10 seconds. Okay. Now, acceleration has a formula, which is the change in speed or velocity. Remember, they're basically the same thing, divided by the time taken for that change. So if we're doing A to B, then the change in speed is 30, because you want from 0 to 30. The time taken was 10, which means your acceleration is 3 meters per second squared. That would be the acceleration during the first 10 seconds. If you wanted to know the acceleration between B and C, I mean, you could do the whole formula again, but the answer is zero, because if you are not speeding up or slowing down, then your acceleration is zero. If you're staying at the same speed, there is no acceleration. So there's none there. Now, if I wanted to work out the acceleration from C to D, now it should be, unless I've got the numbers completely wrong, um, more than the acceleration from A to B. So if I wanted to work out the acceleration here, the acceleration is the change in my speed from C to D, which is 40, divided by how long it took to get from C to D, and it took 10 seconds to get from C to D, which means my acceleration there is 4 meters per second squared. So that is similar to the distance time graph. On a distance time graph, the steeper the line, the bigger the constant speed, or the bigger the speed. Whereas on a velocity time graph, the steeper the line, the bigger the acceleration. Okay, so hopefully that answers the question as to how you work out acceleration from a velocity time graph. Yeah, that's as much as you should ever have to do from that. Um, okay, go back to anything in here that sticks out. Otherwise, what I will do then is, given that someone has asked and I can't see any other immediate pressing questions, is I will do a little bit of a general physics recap. So, because someone has asked me to do the topics energy, electricity, particle model of matter, and atomic structure, presumably ahead of an exam, um, I will do little bits of all of those. Maybe not electricity, but I mean, I'll do what I think is the important some important aspects from those topics. So if I do a generic GCSE physics AQA paper one, if you were doing that recap, it includes topics of energy, electricity, particle theory, and atomic structure. Um, if you have any questions around those topics, then feel free. I'll do my best. But I will tell you from memory the things that I can remember. And bear in mind, this applies to every exam board, whichever one you're doing. But I'll tell you the some of the stuff that I think you should be aware of. If I thought of the topic of energy from physics, then these are the kind of things that I would make sure I'm able to do. So first of all, energy is measured in joules. There are some equations involved in this topic. Now, I appreciate you should get given all of the equations, but there are certain ones. Kinetic energy is a half times mass times velocity squared. There's gravitational potential energy, which is mass times gravity times height. There's also elastic potential energy, which is a half k e squared, where k is something called a spring constant. As I say, you've got these equations. You need to be able to use them, which is a separate challenge. Um, Half-life equations. Yeah, I'll get to that. Yeah, good. Yeah. So these are important that you're able to use them, and you know, crucially, the units involved. So mass, for example, should always be in kilograms. Speed should be in meters per second. Height or distance should be in meters. Mass in kilograms. Gravity is gravity. Extension is a distance, should be in meters. And so these are the little things that, as you may have experienced from the test that you did, the units can need changing. And it's important to get those right. Otherwise, it's easy marks that you possibly lose. Um, the other kind of, I'll give you a important one question that I always explain when I do link these things together. So there is a principle called the conservation of energy, which basically just means that the energy can never be created or destroyed. It's only turned from one type to another. If you imagine the projectors that we use for those people that attend in person, those projectors take electrical energy and they turn it majority into light energy, which shines on the wall. However, you can hear it, so there is a little bit of sound energy, and if you touched it, there would be a little bit of heat energy. Now, the amount of electrical energy that comes out is will add up, sorry, that goes in will add up to the amount of electricity that comes out. So if there's 50 of sound and heat, then that is so the point is the energy is not just doesn't just disappear or get destroyed or anything like that. It basically just always gets turned into other forms. So we just kind of constantly recycle the amount of energy there is on Earth. Um, yeah, so as part of this, the questions that are coming in are helpful because we are going to do some of the stuff that everybody's asking, like radioactivity, in a moment. Anything else? Yeah. I'll just quickly do one question on this, and then I'll move on to the other parts of energy, which is more important, like fossil fuels. Um, I always do this example just because it's a good example that tests your maths and your general knowledge of energy. There is a person here who, let's pretend, has a mass of 50 kg. Um, let's pretend that that person jumps from a height of 20 meters and then lands safely on the floor. The question that you may get from purely from this information is how fast was this person traveling just as they hit the ground. So not the answer is not to zero. So I mean, just as how fast are they going as they reach the ground? And let's do it. So, first things first, we will work out how much gravitational potential energy this person has got. And the way you can work that out is using the formula, which is the mass times gravity times height. Mass is 50, gravity is will be given to you in the question, but we'll use 9.8. The height is 20. 50 times 9.8 times 20 is 9,800. That means this person has got 9,800 joules of energy as they stand at that great height. They will then jump. Now, as they jump, what will happen in terms of the energy changes is that their gravitational potential energy will decrease because they're going to be at a lower height, right? Because it's going to go, what, 19 meters, 18 meters, 17 meters, and so on. So the gravitational potential energy will gradually decrease. At the same time, it's being turned into kinetic energy because they are now moving as they are falling. And by the time they get to the very bottom, the gravitational potential energy will be zero because it will have all disappeared. And their kinetic energy will be 9,800 because the amount of energy they started with must be what they finish with. It's just turned into a different form because of the principle of conservation of energy. So as this person lands, they have got 9,800 joules of energy. I should clarify, it's a maximum of 9,800, but we will assume that for now. And if I know how much kinetic energy a person has got, and I also know how heavy they are, I can work out their speed because kinetic energy has a formula which is a half times mass times speed squared. I take that 9,800 and put it there. 9,800 equals a half times the mass of the person, which is 50, times the speed of this person squared. And then it becomes a maths question, which you should be capable of doing. Half of 50 is 25 v squared. If we divide 9,800 by 25, we will get 392. And then you square root the 392 to get to your actual answer, which is 19.8 roughly. That is how you could do that question as to how fast that person is going as they reach the ground. That's enough on that particular topic of energy. Your energy resources include non-renewable resources and renewable resources. The non-renewable ones are fossil fuels, which are coal, oil, and gas. Please don't forget that. And also, there is one more non-renewable, which is nuclear energy. I think people sometimes just think non-renewable fossil fuels and forget about this one as being non-renewable. Your renewables include wind, solar, geothermal, wave, tidal, probably missed something, hydroelectric. Anyway, there's a few more, right? These are examples of renewable energy resources. Remember, what we do with these things is we get energy out of them. Now, the energy is used for heating. It can be used to make electricity. It can be used to power our cars, essentially. Um, we burn these fossil fuels. And I mean, I don't know how well it's been explained to you, but we get electricity out of this process. A lot of electricity comes from burning fossil fuels because we use the heat to heat up water to get steam, and then that steam turns a turbine, which gets electricity. I won't go into that for now, but the what to be aware of is for all of these energy resources, you want to be able to answer questions asking you what's good about them and what's bad about them, advantages and disadvantages. And some of you, I think the year 10s, had that in the test, had an advantage and disadvantages of nuclear energy in the test. So let's just briefly say, I might not write all of these down, the good and the bad things about some of these things. So fossil fuels, the good, and sometimes we forget about the good because we naturally know the bad things. Good things about fossil fuels includes the fact that they are relatively cheap. We get a lot of energy out of them for relatively low cost. That is the biggest advantage of fossil fuels, and they are reliable. If you have some fossil fuels, they will always give us energy, right? But obviously, and going on to the bad, we know that they are running out because they are non-renewable. We also know that there is a huge consequence in terms of the emissions from burning them. So CO2 emissions from which are greenhouse gases, they contribute to the greenhouse effect, which can cause global warming, which has loads of consequences. I think there's another question. How nuclear non-renewable? Oh, it is, I just told you. Nuclear is one of the non-renewables. There are fossil fuels and nuclear because nuclear energy involves using radioactive material and you do a process called nuclear fission with it. Um, and once you've done that process, you no longer have that material anymore. Non-renewable literally means that you can't reuse the source of the energy. So nuclear is non-renewable. As I said, non-renewable is the fossil fuels and nuclear. Everything else is renewable. Um, what was I saying? Yes. Moving on to nuclear. Good, very similar to fossil fuels in terms of the good, in that they are reliable, relatively cheap, give us lots of energy from nuclear energy. And the other huge advantage of nuclear energy is that they don't release harmful gases. Don't say they don't harm the environment. Too vague. Be very specific. There's no harmful gases being released from that. Okay. Um, and the bad about nuclear is the nuclear waste that has to be disposed of safely. The thing with nuclear waste, and we'll come on to radioactivity in a second, but nuclear waste basically emits radiation, which, if near humans, can cause lots of harm. So we have to dispose of that waste in a safe place, like underground, far away from people and stuff. It's like even when we burn coal, for example, as you have, if you've ever experienced the burning of coal, what do you end up with at the end on the barbecue? Like the ash, right? And you can just throw it in the bin, right? That's what you get. You get that waste at the end of it. Similarly with nuclear, you do get some waste at the end of it. The problem is you can't just put that waste in your black bin, so to speak. It has to be disposed of away from people because it's emitting dangerous, harmful radiation, which can cause cancer and other things. Um, so that's the good and bad of that. With these ones, I won't go into every single one individually, but with the renewables, but the main good for all of them is that they don't release harmful gases, just like for nuclear. So that's the big contrast with fossil fuels. There are no harmful gases released. Again, don't say that renewables don't harm the environment. That is not correct because they do, because it's a very vague thing to do. It's just because you can harm the environment in different ways. It doesn't have to mean the gases. Be very specific. Yeah, they don't release harmful gases like fossil fuels. Um, the they are usually, with most of these, it's quite cheap to maintain them. It just has an initial expensive cost. Like, for example, building loads of wind turbines is expensive, but once they're built, it's not, there's no ongoing cost really. Um, so that's what you want to be able to say. With basically all of them, the bad is usually that they're quite unreliable or they rely on the weather. So wind and solar, for example, don't work when obviously there's no wind or there's no sun. With most of them, there are these kind of sort of disadvantages, but be aware that you can get asked questions surrounding those things. Since people have asked about radioactivity, let's focus on the radioactivity part for the remainder of this. So, and also it connects nicely to nuclear energy. So, in radioactivity, first let's try to explain what is actually going on. And it connects to a chemistry topic called isotopes. You may remember that in isotopes, you learn that isotopes are atoms of the same element which have the same number of protons, but a different number of neutrons. And so, let me give you an example. Carbon, for example, has a 6 on the bottom. And on the periodic table, at least, it has a 12 on the top. But another isotope of carbon might look like this. So these two carbons are different in the fact that this has got 6 protons, that's got 6 protons, but this has got 6 neutrons and that's got 7 neutrons. That's what makes them isotopes. Now, let me add some more context to this. If I had a piece of carbon, then the majority of the atoms, imagine these are all the atoms in that thing. Remember, there's billions and billions of these, right? All these atoms inside this piece of carbon. Most of them will look like this one here, in the sense that they will have 6 protons and 6 neutrons. But some of them will have an extra neutron. So some of them will look like that one. Okay, so they will have an extra. It doesn't necessarily change anything about the carb or the material. It's still carbon. It's just that it has got some isotopes in it. Yeah, I'm for carbon, I'm just illustrating an example here. For carbon, just to show you that when the numbers are different, that's what happens. Yes, carbon can have a 14 on the top as well, so it could have 2 extra neutrons. Just illustrating a point, which is what they are. So the ones that have an extra neutron, whether it's carbon 13 or 14, whatever, those ones can be unstable. So remember, what's happened with isotopes is that the nucleus essentially has got like an extra neutron or two. They can have 2 neutrons extra, in which case that would be a 14, yes. But the point is that the nucleus has got some extra neutrons in it. And what that can mean is that the material is unstable. The neutron does not change the element at all, because the element change is determined by the number of protons, which we'll come to. So these two are the same element because they both have got 6 protons, but they've got a different number of neutrons. But that doesn't change what the element is. It's just that the nucleus is a little bit unstable. We're going to come to the element change because I understand the question. But at this point now, these are still the same element. It's all exactly the same. It's just that there's some atoms in here that have got too many neutrons, and therefore they could be unstable. Now let's understand what we mean by unstable. If an atom is unstable, what it can do completely randomly is emit some radiation. Okay, and that radiation, as we'll come to, can be harmful to humans and stuff, but it can emit radiation completely at random. Now, when it emits that radiation, the reason it's emitting that radiation is to try to go from being unstable to stable. That's what it's really trying to do. It just gives off this radiation. And I'll explain what that means. What it really does is it's trying to change its number of neutrons so that it kind of goes back to where it should be. Do you see what I mean? It's like the atom's got the wrong number of neutrons. It's trying to sort of fix itself. And it does that by spitting out some radiation. Now let's talk about what that radiation is. So there are 3 types of this radiation, as hopefully we know if we've done any of this topic before. The 3 types are alpha, beta, and gamma. And each of them are slightly different, okay, in terms of what they do. Alpha and beta, in terms of equations, are more complicated. Gamma doesn't technically have an equation, so that actually, in a way, makes it easier. Now, as I say, we could have 3 different types of radiation being emitted from an unstable atom. All of them are potentially dangerous to humans, right? That's the point. It's just that there are 3 different types of the radiation. Let's talk about each one. Alpha, oops, is the most ionizing of the 3. Now, what ionizing means is that this radiation can hit other atoms and damage them. That's what I think of ionizing as dangerous, basically. So ionizing means that they can cause harm to other atoms and especially cells. So if it gets into our body, it can really harm our cells. That's what ionizing basically means, causes harm. And just to go to the opposite of that, gamma is the least ionizing of the 3. Okay, that doesn't mean it's not dangerous, just to be clear. It's a little bit complicated, this, I'll get to that. But it potentially causes the least harm, okay? But And that there's a reason for that, and it's what we're going to come to in a minute. So beta is kind of in the middle of those two, so it's all moderately ionizing. It's sort of in the middle. The other thing to know about alpha is it is of the three the least penetrating, whereas gamma is the most penetrating, and once again, beta is sort of in the middle, which we'll talk about later. Um, what that means is that it doesn't travel very far and it can't get through materials. Alpha radiation is basically stopped by a piece of paper, whereas gamma can pass through paper, it can pass through most metal. It's needs what we need is a specific thing to stop it. Um, thick, thick lead. So a thick material is needed to absorb and stop gamma radiation from passing through it. Whereas alpha, you don't need much at all. It can't pass through something as thin as a piece of paper. Beta is again sort of in the middle, so it's moderately penetrating. It can pass through the piece of paper, but it would usually be stopped by some thin metal. And beta, as I say, is moderately ionizing. It is slightly causes more harm than gamma, but less than alpha potentially. So this little summary that I've just done here: alpha, most ionizing, least penetrating; gamma, most penetrating, least ionizing. That is important for most questions on this topic to have a good understanding of. Now let's just talk about each of these in turn and explain what they actually are. So, right. So again, if we just go back to that illustration quickly of the atoms, right? Let's pretend that these atoms here were unstable. So they had too many neutrons, they were isotopes essentially. And they will randomly give off radiation. Let's pretend the radiation they're giving off is alpha. What does that actually mean? Right. It means that when alpha radiation is emitted, it means that an alpha particle is like spat out, is emitted from the nucleus. And what is an alpha particle? An alpha particle is two protons and two neutrons. Think of them as just being stuck together like in a ball. So it's like, let me do this properly. P, P, N, N, right? That is essentially an alpha particle. It's two protons and two neutrons, and they are spat out of the um, nucleus if it's undergoing alpha radiation. Okay. Now, this does create questions where you get these equations involved. So look, if we just go back to that carbon quickly and say it was 6, and let's say that was 13, for the sake of it, right? Yeah. Now, if it emits an alpha particle, right? So if it emits an alpha particle, that means that it will get rid of two protons and two neutrons. That's what it's getting rid of. Now, if it gets rid of two protons and two neutrons, what happens to these numbers? Well, firstly, at the moment, it's got 6 protons and 7 neutrons, right? What will it have when it spits out two protons and two neutrons? It will only have 4 protons and, can't do the maths, 5 neutrons. Okay, so it will, because the number of protons has changed. Remember, that's what that question that someone asked about um, the element change. Well, now the element changes because the number of protons changing is what makes an element change. The neutrons changing actually has no effect on the element itself. The number of protons has changed. So that carbon will actually no longer be carbon. It will be whatever has a number 4 on the bottom, which I can't, off the top of my head, remember what has a 4 on the boron or something like that. I can't remember. Boron, I think. So whichever number has a 4 on the bottom of the periodic table is what that ends up turning into. Um, so that's what it is. Now let's put this into a proper equation as to actually how you actually get shown it. So this is how it will be shown. So there will be an element, 6, 13, let's say. Sometimes they don't even give you the element. It doesn't, sometimes they don't, but yeah. And now if it undergoes alpha radiation, this is what the equation will look like. So you'll have a new element here, and that new element will have a 4 on the bottom and a 9 on the top because look, what is that top number? The top number is the mass number, right? It's the sum of the protons and the neutrons. Now, the protons and the neutrons only add up to 9. So effectively, we've reduced that by 4. Um, and so that's become a new element. Is it boron? I don't know. I can't remember. Whatever it is, it doesn't really matter. But what we need to know now represent is the alpha particle that's been emitted. Now, there's two ways of representing the alpha particle depending on your questions, right? So sometimes they use that symbol for the alpha particle, but they ask you to fill in these numbers. Now, those numbers have to be 2 and 4 because it needs to add up to what you had here. So the 9 add 4 is 13, and 4 and 2 is that. The reason this is often shown here is because effectively what do a 2 at the bottom and the 4 on the top mean? They mean 2 protons and 2 neutrons, don't they? Because the number at the bottom is the number of protons, and the number at the top is the 2 things added together. Is it BE? Okay, fine. Yeah, fine. Electrolysis, I don't think we specifically do electrolysis until year 11 in terms of our normal classes. However, what you can do with these things is firstly, there's two ways. Obviously, there are videos that I have made on electrolysis, but if you just let us know in advance, then I can do it in one of these sessions. I don't have any problem with that. We can just do it. I won't do it today, but I can just do it. Do any of the topics across maths or science, anything. If you sort of let us know beforehand, then I can sort of plan it and say, okay, well, we'll do that. Ideally, we would do it in the chemistry week. So, for example, next week we're doing maths, but in a few weeks' time we do chemistry again, and I'd do it in that. But I can always adjust whatever we're doing. With these online things that we're doing here, as I say, I'm completely flexible with it. Happy to do some homework questions, and then whatever else, if I can be of assistance, I will do it for some time at least. So, that is how you do it. Now, the other thing that sometimes an alpha particle is shown as, just to tell you, it's sometimes represented with the helium's atomic symbol, because helium has those numbers, and it is the nucleus of helium contains 2 protons and 2 neutrons. So the nucleus of helium is effectively the same as an alpha particle. That doesn't mean an alpha particle is helium, because helium is made up of the electrons and all the other shells and stuff. So like just the nucleus of helium is kind of the same as um, an alpha particle. So sometimes this thing here will be shown with a helium He, just so you know. But when you see these questions with these equations in radiation, they couldn't be really much easier, because the thing that they're really testing you on is not actually the element that it turns into. I know you just said it's BE, but that's not actually what you're being tested on. It is whether you know what numbers go here. And those numbers that go there need to just add up to the number that you started with. Or if there's a gap here, then you know that the numbers add up to it. So 9 add 4 makes 13, and 4 and 2 makes 6. So that is all of that. Yeah, in terms of the electrolysis before 17th of Feb, just send us an email at some point nearer the time. And yeah, it's not a problem. So that is an equation involving alpha particles. Okay. Right. Let's just do beta, because beta is a little bit more complicated. Alpha is relatively simple because it's always just like this 2 and this 4. So 2 protons and 2 neutrons makes 4 on the top and 2 on the bottom. So it's always that. And the numbers kind of just are fairly obvious, right? It loses 2 protons and 2 neutrons, so the numbers change accordingly. Beta, a little bit more complicated, because when beta decay happens, so instead of alpha radiation happening here, some things will have beta radiation. When that happens, beta is when and this is confusing to explain, so don't ask me to explain it further. It's when an electron is emitted from the nucleus. Okay. Which, if you think about it too hard, doesn't make any sense. So don't think about it too hard. But that's what happens. A beta particle is just an electron. That's what a beta particle is. We often say it's a high-speed electron. I don't know why, but a beta particle is an electron. Now, So when beta decay happens, an electron is emitted from the nucleus. However, this is the important bit to remember. Not only is an electron emitted from the nucleus, but a neutron turns into a proton. And it's the changing of a neutron into a proton that causes an electron to be spat out, so to speak. Um, and that makes the equations a little bit more complicated because let me explain. So if we just do the same with carbon, just I'll keep using carbon because I've just got the numbers um, in my head right now. So let's say we've got carbon and it now undergoes beta decay or beta radiation is emitted. Now that means that, remember, we only care about the nucleus. So yes, an electron is emitted, but that doesn't change anything. The thing that actually changes the numbers is this bit here. So a neutron turns into a proton. So what's going to happen is we're going to give out an electron. An electron, we always write like this. We put zero on the top because electrons have basically got zero mass. And we put a -1 on the bottom to show that that's basically what a charge of an electron is. So for alpha, we use the numbers 4 and 2. For beta, we use the numbers 0 and -1. Okay, that's what we do. And then beyond that, right, surely, again, if we just follow the same principle, that the numbers need to add up, then it should be quite easy to know what numbers go on this missing thing here. Because there's a 0 there, this will still have a 13 there, because 13 add 0 is 13. The number that goes there, though, has got to be 7, because 7 -1 is 6. And again, the numbers just add up. It's just that this time there's a negative to think about a little bit. Now, in this case, and because that number has changed now, again, the proton number is what determines a change of element. The element now is nitrogen in this case, but I mean, it's not the element itself doesn't really. Is a beta particle not a fast moving? Yes, that's what I said. Yeah, so a beta particle is a fast moving electron. But the important thing about beta, yes, the electron is what's emitted, is how that affects what's left behind. So what's left behind is a neutron turning into a proton, which is why, if you understand that, these equations can make sense. So what's actually happened here, just so you understand the numbers, we started with 6 protons and 7 neutrons. Now, if a neutron turns into a proton, what do we have with the number of neutrons? It becomes 6, doesn't it? And what happens to the number of protons? It becomes 7, which is why these numbers make sense, because the bottom number is the number of protons, and the top number is the sum of the protons and the neutrons, which hasn't changed, right? A neutron turning into a proton doesn't change your mass number because it's still the same total sum of protons and neutrons. And that is how you do these equations. Okay. There isn't one for gamma because what gamma is just, as you potentially know from waves, it's just some electromagnetic radiation. So that's what it gives out if it's emitting gamma. It doesn't actually change, at least as far as you need to know, anything in the nucleus, and there's no equations therefore relating to it. There were other questions on this topic, which were something to do with half-life, wasn't there? Radiation half-lives, equation of atomic structure. Right. What I'm going to do to explain half-life, some of you will have seen this before, which is a picture that I like to demonstrate half-life with. I actually need to go to my correct notes to get hold of this. Okay. Right. I'm going to start with a picture that I'll put it into a definition later. But what you can see here is a little bit like, when I showed you earlier, I showed you a bit of carbon and I said some of them are isotopes which are unstable and so they will give off radiation. This is the exact same image, essentially, where as the labels show, in this, imagine this is one piece of carbon or whatever, and these are all of the atoms in it, and all of the white circles are stable, which means that they don't are never going to emit any sort of radiation. They're just going to enjoy life and stay as they are. The pink ones are unstable, which means that they perhaps have too many neutrons because they are isotopes. And that means that at some point, randomly, they will emit some radiation. Now, the thing that I didn't say before, which I should say now, is that once an atom emits that radiation, whether it emits alpha, beta, or gamma, it just does it once, which means that after it's done it, it becomes stable. Remember, the reason it's trying to do it is to become stable. So once it's done it once, it basically is done. Okay, so it changes from being unstable to stable effectively. So once this gives out some radiation, it is now not going to do it again. So, which means that these are randomly going to be giving out some radiation, but once they've done it once, they don't do it again, which means that the radioactivity of any material, the amount of radiation it gives out, always decreases with time. So, if I've got a calculator here in front of me, right, which has got some radioactive atoms, it means it's giving off radiation, but it means that it's constantly giving out slightly less all the time because each time it does it once, or any of the atoms do it once, they don't do it again. So remember, whilst this picture shows, whatever it is, however many, 50 of these circles, there are billions of these atoms in any material, billions and billions, loads of them. And so when some of them are giving off radiation, it's like it can seem like lots of radiation is being given off because they're all sort of doing it at the same time. But over time, once each one has done it, it doesn't do it again, which means the overall radioactivity has to decrease with time. Every radioactive substance eventually basically doesn't give it out anymore. It becomes safe because it has to gradually decrease. So this image just sort of simplifies that whole thing. Someone asked me a question. Um, give me a minute about the half-life from a graph. I'll get there. Um, so once this pink one gives out some radiation, effectively it becomes white. Okay, because it changes from unstable to stable in the purposes of this picture. Now, at the moment, there are 24 pink circles here. I know because I have done this before. There are 24 pink ones. Okay. Over time, each of those pink ones will give out some radiation and become white or stable. So that means the number of pink ones here is reducing over time. The pink ones basically represent the radioactivity of this material, how much radiation is being given off. After a certain amount of time, those 24 at some point in time will become 12, won't they? Because they're just decreasing over time. So what's happening here in this picture on the right is that there are now only 12. So half of those pink ones have given off their radiation and are no longer giving it off anymore, or they're stable again now. Now, however long that took for those 24 to become 12, however long that took, is called a half-life. With different materials, it takes longer. With some, it takes, minutes. But however long it takes for the amount of radiation to halve, or the radiation being given out, or the unstable nuclei to halve, is all the same thing, is called a half-life. Now, as I said, for some materials, that could be millions of years. It could take millions of years to go from 24 to 12. It could take 10 minutes to go from 24 to 12 for a different material. Whatever that is, we call that, in general terms, a half-life. Now, the important thing about this is that however long that may have been, let's say that was 5 minutes. So after 5 minutes, the radiation went from 24 to 12. It halved. After another 5 minutes, it will halve again. So the half-life is the same for every material. It's just the amount of time it takes for the radiation or the radioactivity to halve. So after another 5 minutes, what will happen to that 12 if the half-life is 5 minutes? After another 5 minutes, the 12 ones, unstable ones, will become 6 unstable ones, will they not? Whatever that half-life is, as I said, it could have been 5 minutes, it could be millions of years, but that is what it is. So, and it does take a while to get your head around, especially because questions on it can be weird. I'll go straight to a question on the graphs first, because it's actually easier to do half-life from a graph than it is to do it without one. So what this is showing you is a graph of the activity, and that's how we measure radioactivity, we call it activity, over time. And as I said, with any material, this will always be a downward graph because the radioactivity has to decrease over time. We start off with loads of it happening, but once it happens, it doesn't happen again with each nucleus. So it gradually decreases over time, as this graph is showing. Now, if you want to measure the half-life, all you do is you look at this value here, which is the beginning of this graph, and you go to half that value. So in this case, 40. And you read across from there and read down to the time it took for that 80 to become 40. In this case, it was 4 hours, because it's in hours, and therefore the half-life is 4. And you can check it, because it should, after another 4 hours, the activity should halve again to 20, right? So after 8 hours, you can see the activity is 20. It halves again after another 4 hours. So that every half-life graph actually looks like this. It has to have this shape. It will always be steeper at the beginning and then less steep later. We saw this in that forces question, where it's dropping, in this case, dropping more quickly to start with and then not dropping as much, because half of a big number is bigger than half of a smaller number, right? 80 to 40 is a bigger drop than 40 to 20 and 20 to 10. So it will gradually always have this shape. So that's how you tell half-life from a graph. I'm going to do one more question on this, and then that'll be it for today, I think. To show you that half-life questions are not always that straightforward. So, and this is what I will do. Yeah, this one. In fact, I'll do a tiny bit more. I've got something else to say. It says that the activity of a radioisotope is 640. So you can think of that as being 640 of those pink circles in that diagram. It says 2 hours later, the activity has fallen to 80. So 2 hours later, effectively, those 640 pink ones are now 80 pink ones. The question is to work out the half-life based on that. So I'll tell you how you do it. You say that, okay, if I've got 640 now, then after one half-life, whatever one half-life is, I don't know what one half-life is, but whatever that time is, it will have halved, right? So 640 will halve to 320. After the same amount of time, another half-life, it will have halved again, and it will be 160. After another half-life, it will have halved again, and it will be 80. So to go from 640 to 80 is 3 half-lives, right? 3 half-lives. We don't know what half-life is, but we do know how much time this whole thing took. It took 2 hours. Okay. So 3 half-lives are the equivalent of 2 hours. And 2 hours, we'll put it into minutes just for ease, is 120 minutes. Which means that if we divide by 3 now, because a half-life is always the same, one half-life must be 40 minutes. And it is quite difficult to get your head around these questions. But if you understand that, then hopefully we're okay. Last bit of this, I'm losing my voice a little bit, is the difference between 2 words, which I just want to tell you: irradiation and contamination. Irradiation is, let's imagine this situation. As many of you know, I cannot draw, but let's pretend that this is some dangerous radioactive material and you are this close to it. You're in the same room as it and it's giving off radiation. Now, if that is the situation where you are exposed to some radiation, you're in the same room as it, which means this radiation can hit you, as it were, we describe you as being irradiated. So irradiated is just being near a radioactive source, so you can be exposed to the radiation. If you didn't want to be exposed to the radiation, you need to put something in the way, a barrier like lead and stuff, like the stuff they do in X-rays, that stops the radiation getting to you. But if that is a situation, you are irradiated because you've been exposed to the radiation. Whereas, in order to be contaminated, what you need to do is be crazy enough to handle the material with your hands. Okay? This is described as being contaminated. Okay? So contamination is when you've actually touched the radioactive source. And when you touch it, because remember, atoms are so tiny, they're impossibly tiny. When you touch anything, some of the atoms from it rub off onto your fingers and hands. And so what's happened is you've ended up with these radioactive atoms on your skin. And the natural progression from that is that it ends up in your body. The material ends up in your body. That's the crucial thing, not the radiation itself, but obviously that does as well. But the actual atoms that are giving off the radiation end up in your body. So you have this like something in your body that's giving off radiation because as soon as you get something on your hands, it essentially will end up in your body either through your skin, or you just touching your face or eating food or whatever, it will end up in there. And so it ends up in your body. Now, there are differences between these two as to their respective dangers. Contamination generally is much worse, which is why you should wear gloves when you're handling things. However, um, what you need to know is that if you are irradiated by something, then it's more dangerous if it's beta or gamma radiation that is being given off. Why? Because beta and gamma are more penetrating than alpha, which means they can get through your skin. Alpha won't pass through your skin. So if you're in the same room with something giving off alpha radiation, it's not great. You don't want to be in that situation, but it is not as bad as if it was beta and gamma, because alpha will hit your skin and it'll never be able to pass through it, whereas the other two can. So if they can pass through your skin, they could enter your body and they're more likely to be dangerous. Whereas if you are contaminated by something, alpha becomes the most dangerous because it's the most ionizing. So it can damage your cells from the inside, but also because it doesn't pass through stuff easily, it's not going to get out of your body either. It's all going to be stuck in your body, bouncing around and damaging loads of things. Whereas beta and gamma, if they end up, if something's giving off beta and gamma and it's in your body, then that radiate again, that's not good. But at least the radiation is likely to pass out of your body. If it's heading in one direction, it'll keep going out of your body. It could do some damage on the way, but it will leave your body because it'll pass out. Whereas alpha won't, and alpha causes loads of damage in a small area. So often a question that I often ask people is which is the most dangerous out of alpha, beta, and gamma? And often people naturally go straight to either alpha or gamma, depending on what they think. But the answer is always it depends. It depends whether you are irradiated or contaminated. If you're irradiated, then beta and gamma are more dangerous because they can pass through your skin, alpha won't. But if you're contaminated, then alpha becomes the most dangerous because it's more ionizing and it's inside your body and it won't pass out of your body, whereas beta and gamma will probably pass out of your body. Um, that largely covers the topic of radioactivity. There is a little bit more to it. Nuclear fusion, nuclear fission are these extra little bits that are, depending on which one you're doing. I won't go into them for now. I think that is hopefully sufficient for today. If you do have any other questions, then feel free to email us. If you want to let me know in advance of any of these Wednesdays of something that you want to do, then that would be helpful. I will have the homework each time ready, but if there's anything in addition to that, it would be whilst I am very much capable of adapting to whatever you ask, if it's sent beforehand, it could be quite helpful. So, on that note, assuming there is nothing else, I will let everybody go, or I will go, and I will see you all when I see you.